due to the obviously popular demand, I've tried to accommodate some of the comments. As you know, instead of seminars, I've been bringing in more of the old style lectures back on board. This is completely old style lecture. Okay? We're going to talk about the physics of additive manufacturing. So mainly talk about the different heat sources. We're going to talk a little bit about the melting, the physics of melting and solidification. We're going to talk about convection and conduction. So the three main modes of heat transfer and how they affect some of the final built-up layers in additive manufacturing, particularly from the metal perspective. So there's a little bit of everything going on in additive in all the main processes that we've been looking at on the metal side. We've got a heat source, which can be typically electron beam or optical laser based, which gives us a source of radiation, and the interaction of the material, the absorption and the reflection of whatever material, whether it's a wire feed, powder, will determine how successful the heat source is in melting and creating a melt pool. Typically in the processes, whether when there's a gas used, an argon or some inert atmosphere, there'll be gas flow, and that will create a forced convection, which will typically be used to take away some of the condensation of metal sort of nanoparticles which come off and plumes that come off. But that itself is a form of phase change in the material, sometimes unwelcome, but sometimes part of the process is the evaporation, which will lead to those keyhole modes which we looked at. So the gas is typically used to cover that up, take away the condensate, but obviously the most important thing is the actual melting and solidification, which depending on whether it's wire or powder will have a different form, but will always be very similar to what you see with standard welding. Because we're melting and solidifying, that also being another type of phase change, the predominant phase change, it means that when it resolidifies, you often get shrinkage, and that shrinkage can lead to porosity. The conduction is important, so it determines the rate at which the heat is transferred away from the melt pool during the solidification. It determines a lot of the aspects of the solidification. So, but conduction can also play a big role in the actual pre-sintering, like in the electron beam process. We've got sort of the thermofluidic aspects to consider, which will be surface tension based, wetting and de-wetting, capillary flows and Marangoni convection are all parts of, convection, which we're going to talk about a little bit. We've also got a discrete nature of the powder side of the flow, so when you're pouring particles down a hopper and they settle on a base plate and into the powder bed, they may segregate. So there's a sort of a density-driven segregation of the actual discrete particles as they come into the bed. So because of that densification, and you get a sort of stratification of the powder, that itself can lead to sort of differences in properties and melting during the different stages. And that's pretty much, you've also got the wiper plays its own role in wiping the powder across the bed, also leads to the segregation of the powder. So a lot of different aspects. But what we're going to have a quick look at is how, what types of different heat sources, and I've got a few. We've seen this before, in the actual classification of the metal systems. Primarily either we'll have a beam-based laser beam or electron beam, or there'll be sort of arc and TIG weld and MIG and plasma welding working on the wire side. So look at some of the electron beam. This is the Sciaky wire system, and you can see the wire is coming through the rod, and following it on the top is the electron beam pointing down at the same local area where it's landing. Then we've also got another electron beam system, which also uses the electron beam as the heat source, which is actually in the powder bed system. This is the one that Colin Cater was talking about when he worked at ARCAM. And how it works is that you've got two powder hoppers, one on either side, and a spreader. You've got a pre-sintering stage, and then you've got the beam stage, which if you zoom in and look at how the pre-sintered particles are then melted into a layer, and then that carries on in a normal way with a powder bed, that layer drops and it builds up an entire component. Laser deposition. So this is from a video by Trump, and you can see the powder is sent down coaxial through the nozzles, and then the laser is sent down through the middle, and they hit at the same point, and that enables it to deposit layers. And this is on the end of a robot arm with a number of different degrees of freedom. A lot of different lasers can be used with these laser deposition systems. So depending on the application, on whether you need to have a really high, large surface area, or if you're looking for more fine detail, the larger surface areas will be covered by more powerful CO2 type lasers with a larger wavelength. And then sort of finer details, thinner clads will be done using similar ND-YAG or even ytterbium fiber lasers like the ones that they use in the powder bed. Another powder laser deposition system. This one uses the a ytterbium fiber optic that was the system by beam. A very similar system. They feed the powder down through the nozzle, which converges at the same point as where the laser is hitting to enable them to sort of draw lines. And they can get through being able to move both the laser head and also the component part. They can get quite complex shapes. So this is the lens process, which is also very similar. This is the American equivalent, probably one of the first ones around. And this just shows some of the thermal imaging. So you can see the melt pool progressing with a, you can see the hot spot and then the tail of it at the back. And that's building up a wall there or something simple. So now we'll get on to the powder bed, laser powder bed fusion. And this is a video from the SLM, which is the German kind of equivalent of Renishaw. They are showing on this video here how they're trying to control in situ or actually monitor the melt pool in situ to try to control the process even tighter. And I think they're using this in this system. They're trying to use some of the gases, some of the evaporates that come off from the melt pool. There's a new sort of monitoring system. So you've got all these different heat waves that come off of them, and they're scanning them with a second optical laser, which then goes back up through the focus lens and is reflected back to the main system. And then analysis is done on that, and it will correct the settings of the laser. This is some of our own footage from our own system, looking at the powder bed in process. So this is taken with a high-speed camera, looking down on that's about 10 millimeters by 20 millimeters. It's being colorized according to the intensity of the light. But there is quite a bit of a connection between the intensity of the light and the temperature of the melt pool. So you can see quite intense where the laser is directly hitting. What you can see though, as you start to get closer in on the high-speed images, is that the process is actually a lot more I would say it's almost like a volcano. It's much more explosive than you think of. When you think of welding, you sometimes think of it as a relatively tranquil process going back and forward. But when you've got powders and you've got gases and you're down to that sort of level, you can see that there's a lot of things going on in the melt pool which are not easy to capture using finite element models or anything like that, things that we don't really understand that well. So you can see some of the larger particles being expulsed from the melt pool. That's through a mixture of some of the gases, and the porosity was there in the powders, and the melt pool just blowing it out. You can also just about see a trace of some of the plume which is forming from the plasma that forms just above the melt pool, and the condensate that forms and is being taken away. And that's the gas is doing its job. It's taking the condensate away and it's putting it into the filters. Some more thermal imaging on a Renishaw machine. This isn't actually one of ours. It just shows you on a number of hatch patterns some of the sort of the temperature build-up and how it cools down behind it. And you can see that last flashes when the laser goes around the outer contour of the hatch pattern to finalize it. There. Okay, so now, like, zooming in even more into the melting process, this is some work done over in the States, and you can see three different materials, three different settings on the same material of 316L steel. So there's a 200 watt with 1500 millimeters per second, 300 watt with 1500 millimeters per second, and a 200 watt with 2000 millimeters per second. And again, it shows you now really, this is literally looking down probably at about a field of view of about 100 microns. So it's right down at the level of the laser hitting the powder. And it now really doesn't almost even resembling a welding process, although it is a welding process going on. You can see the laser going from left to right. You can see the main part of the melt pool, but what you can also just about start to make out there is that you've got an effect called the denudation of the powder. So what's happening is that as the melt pool is going along, it's actually gathering powder from around it and pulling it into the melt pool and forming a bead on the top. So if you were to do, that's often why you need to have quite a lot of powder and a relatively wide hatch spacing in order to be able to get these things to overlap, these tracks to overlap. Okay, so that was reality. Now I'm going to take you a step back to look at the maths. So it is possible, it's one of the things we're trying to do at Swansea, but it is possible to detach the fluid dynamics and the heat transfer. And this is very much dominated, because of the heat sources being quite powerful, it is dominated by the heat transfer, but the fluid dynamics is in there. So what we've got is the Fourier, the heat equation, and you've got the left-hand side, which carries the convection diffusion terms, and then you've got your conduction terms on the right-hand side and your radiative heat source terms on the right-hand side. That just defines the transport of heat within or underneath the zone of the laser. The first part, you have density times specific heat capacity. I'm sure you've seen this equation before. Hands up if you haven't seen this equation before. Is that a mean question to ask? You will have seen it before, and probably in its simplest form, it's actually quite solvable. What you can see on the left-hand side of the equation, so you've got your time dependence of the temperature. You've obviously got a moving laser, so you do have a transient time, but you've got a velocity vector u. So this heat equation is actually valid for both the fluid side and for the solid side. On the fluid side, you've got movement of the fluid, which is defined by the velocity, and that also transports heat. So the fact that the fluid can be moving, that takes heat from one place and puts it to another in the fluid part. In both the solid and the fluid, you've got heat conduction through the solid and you've got heat conduction through the fluid. So that lambda there is the thermal conductivity, and thermal conductivity can be anisotropic, which is why it's still on that side of the gradient term. This gradient term is actually, if we had a constant lambda, it would be del squared T, which is the Laplacian of T. So it comes down to quite a simple heat transfer equation. Q is a surface-based source term of heat, which will drive the equations. If you're dealing only with a solid, that second term there, that U dot delta T, disappears. Okay? So this equation can be used to work out some temperatures. You can solve it analytically, and that's been done for welding for many years, going back to the 50s. you can actually solve this analytically on a half plane using classical solutions for welding, like the Rosenthal solution. I'm not going to do any of that now. It's not a maths course, so I'm just giving you some of the physics of the equations just to sort of understand them when you see them. These are just definitions of conduction, radiation, and convection. So just to make sure that we all know what we're talking about in terms of the conduction, occurs within all phases, be it liquid or solid or gas, because of heat gradients, and is fundamentally due to the collision between molecules, the migration of free electrons. That's conduction. Radiation occurs by emission of electromagnetic waves from any heated surface and can be transmitted through all phases, or even without material. So even if you're in a vacuum, you can get radiation heat transfer, that's what it's saying as well. So convection is mainly an interface between liquid, gas phases and solids on the fluid side. So that's mainly convection's on the fluid side. But it can arise from a number of different. So often when we think about convection, we think about either natural convection or forced convection. But convection can also be driven by compositional changes, and that's partly what we're going to see can affect the melt pool. Right, so a little bit more about E-beam. We've seen the videos, and Colin gave us a little breakdown. So I'm not going to pretend to know everything about this system. I've never actually driven one. I've seen parts that come out of it. But with this, you're basically making a stream of electrons from a heated filament at a very high temperature. And then instead of having lenses, we have magnets which focus the electron beam. And we have another set of magnets which drive the focused electron beam onto the surface. So very similar to a laser with lenses. That's what we're doing. We fire the laser down. We have galvanometers and mirrors which move X and Y, and then we focus it through a lens and we converge it onto the plate. With this, we're converging it using magnets. And of course, then the electrons actually hit the top of the powder and they heat it up to melt it. Okay, so what we did see with the ARCAM EBM system was that there are actually two containers, one on either side of the powder bed, and both of them tip out together, and you have a spread from both of the hoppers. I just thought I'd make sure that some of the details of the EBM system were down in writing. So they make a couple of different systems, the A1 and the A2. The A2 system is slightly larger parts. One of the things that you do see which are quite distinctive about the electron beam system, first of all, we tend to have surface roughnesses. So this RA was a measure of surface roughness. That's 25 microns and 35 microns. It's quite a high roughness for a process, which should be compared to our powder bed process, which is more in the region of about 12 to 15 microns on finished parts. It's not to say you can't polish it. You can polish it. Now the beam power is significantly higher in terms of watts, but then of course this is an electron-based system, so it doesn't have exactly the reciprocal of an optical-based power rating. The beam spot size is a lot larger than what we work with in the powder bed, laser powder bed system. So this is about a 200 micron or 0.2 mil minimum, up to 1 millimeter. So those are large spot sizes. With the powder bed systems, we'll go anywhere from 50 microns to maximum of about 150 microns. So our spot size is a lot smaller. And to go with that, our powder sizes in the laser powder bed systems are a lot smaller as well. So we'll typically have powders at the 15 to 45 micron range. But the electron beam powders will be 45 to 100 microns. So there's a number of differences there. What they do get with the electron beam systems, they have much higher build rates, much higher speeds. So they can scan up to 8,000 meters per second. I think that's supposed to be millimeters, but I could be wrong. But even if it were millimeters per second, that's still 5,000 odd millimeters per second higher than what we do in our. So their build rates, the rates at which they build each of the layers are much, much faster. It works under vacuum as well, which is the thing that Colin pointed out the other day when he was here. And because they work under vacuum, they have problems with being able to do very light materials like aluminium, which will vaporize under the electron beam. So here's some very basic sides. You probably know most of this already, so I'm just working my way through a series of different lasers, just defining what the electromagnetic radiation is, what light is, and the range of, when we talk about optical lasers, the sort of ranges we're talking about there, UV, Vis, and IR, and maybe, but not microwave. Some other things that we need to get relatively accustomed to working, to know a little bit about when we're working with lasers, are length scales that we're not used to as engineers. So, I mean, typically we'll work in meters, millimeters, maybe micrometers if you're a materials person, but when you start talking about nano, pico, femtometers and all those, we don't really tend to know all those. So I've stuck them in there just because some of the attributes of lasers we're going to deal with later on have some really peculiar length and time scales. So time scales as well, we will typically deal with everything above 10 to the minus 6 second, but everything below that is kind of obscure to us and in the realm of solid state physics. But we need to know a little bit about it because the pulse width of the lasers, which we're going to see, sometimes use these things. So laser stands for light amplification by stimulated emission of radiation. And it's different to white light because it's monochromatic and coherent. And what do we mean by that is that it's the wavelength of the lights coming out of it are in the same phase, both temporally and in space. It's monochromatic. It doesn't have. It has one single color. And there are a number of different lasers. This is a gas laser. So again, I'm really not going to pretend to know everything about lasers. I just have to know what I need to know to get the kind of work that we do done. But the idea is that you're going to somehow excite the molecules inside, for example, on this gas laser, using electricity to somehow excite them, and you're only going to let them out, and they're going to bounce around in there, building up energy inside, and you're going to basically pump it, and that's going to allow eventually for bursts of light, which is both monochromatic and all heading in the same direction, basically. So the different types of lasers, gas lasers, liquid lasers, solid state lasers, there's also disc lasers, and there's a lot of different lasers that have been put together. The lasers can be in both continuous and pulse mode. We're going to focus on the industrial lasers, which is primarily the ones that we're interested in will be the CO2, ND-YAG, and the fiber optic lasers. So the same kind of excitation can be done within a solid as well, using certain crystals which have been perturbed with a small amount of some of these rare earths like terbium and erbium. So the reason that the terbium fiber lasers are the most used at the moment is they are, through one thing or another, very efficient electrically. They're relatively cheap, they're robust. They are certainly much more efficient than the YAG and the CO2 lasers. So those things count. Also, at the level of the wavelength that they work at, they work better at melting small amounts of material within the spot size that they work with. So the pulse. So the two things with the lasers that have evolved, and one is the pulse duration. So that's got shorter and shorter, and the other thing as well is the wavelength. They've changed as more lasers have been, having started with the gases and going on to the sort of solid state ND-YAG type lasers. The typical wavelengths that we're interested in with what we work with on the optical side are between 1 and 10 microns typically. That just shows a snapshot from Wikipedia, and this gives you the sort of bands, the wavelength bands are here in the sort of near and far, mid-far infrared. So you can see the CO2 on the far 10 micron band, and then you'll find somewhere in there the ytterbium ND YAGs and the ytterbium fiber lasers will be around the 1 micron band. So varying the intensity of the laser and also the pulse duration allows you to do different things with them. So some of them will be better if you want to have a very short pulse width and a very high intensity. You'll be looking at making holes in your material, ablating it, which is certainly something that we wouldn't want to do. We want to be somewhere in this region, sort of mid-range intensity and mid-range between excitation and melting. So literally heating and possibly just about homogeneously melting our material. So whatever source of heat that we're using, so whether it be electron beam or optical laser, does define the interaction with the material. So that defines what the melt pool will look like. You've seen through some of the process maps that we looked at last time that there were essentially a couple of different areas on your process map that you wanted to avoid, and one of them was kind of overpowering the melt pool and forming keyholes. So with the keyholes, you're evaporating material which needs to be carried away, and you're also creating potentially porosity and adding porosity into your parts. But also, if your power density isn't right, you can also have balling effects. So if it's going too fast with not enough power, you'll end up heading towards balling effects. So you need to get a balance, and that depends very much upon the heat source you're using, but also on the properties of the material, and also how it's cooled and how the gas goes over it. So all of these things combine together. Just some of the basics of, just run on to the next part, which is on the melting and solidification. And each of these different sections I've tried to kind of pinpoint why it is that they are important, just to know a little bit about in terms of additive manufacturing. So here I'm going to talk about not just specific heat, but we're going to talk about phase change, liquid as solid as latent heat, all things which are probably very familiar more to materials students possibly than mechanical. But we'll talk about the crystal structure of metals as well, which is very important in terms of their mechanical properties. And a lot of these are dependent on heating and cooling. So specific heat capacity is the amount of heat required to change the temperature of 1 kilo of a substance by 1 degree Celsius, standard thermodynamics. So EH equals specific heat capacity times mass times the change in temperature. Okay? Heat energy in joules, mass in kilos, change in temperature in Celsius or Kelvin, and that's your specific heat capacity there. And units are joules per kilogram Celsius or joules per kilogram Kelvin or kilojoules per kilogram Kelvin or Celsius. I'm sure that you have seen all this before, but this is the basis of phase diagram for alloys. So just to point out, when you have a pure substance, if you've melted it and you're coming back down on the temperature time curve, you'll have a cooling rate. That plateau that you reach as you go through a phase change between the solid and the liquid, is over the freezing range. If you have a pure substance, that's a flat plateau, and the duration of that and the size of that plateau is determined by the latent heat. Okay. Once the latent heat's been overcome, then it goes back to solidification and it goes into the solid phase, and then eventually your cooling curve will join the original cooling curve. Now, for an alloy, pretty much the same thing, except the solidification of the alloy happens and the phases fall out. So some of the phases want to freeze earlier than others, and because of that, you've got a line. It's not a straight flat curve. The duration of the time is still dictated by the latent heat, but you have 2 points rather than having a single point. You have your solidus and you have your liquidus. And your liquidus is the higher temperature. Your liquidus is the point at which your liquid first starts to see the onset of freezing. Your phase started falling out. You go into what's called the mushy zone when you're talking in casting. And eventually you reach your solidus temperature. And your solidus temperature is when the entire, all the phases that may be in there in that alloy have all solidified at the same time. And then after that point, you've got a solid. There may still be some other solid phase transformations, but on the whole, that will try to join up with the cooling curve it was originally going down on. So now we've got to capture that, the latent heat is defined as the energy that is lost from the object during solidification. So the specific latent heat diffusion of a substance is the heat energy required to change 1 kilo solid at its melting point to 1 kilo of liquid without there being a change in temperature. Okay, so in the same way as we have with the specific heat capacity, the heat energy is mass times specific latent heat. And again, the units of latent heat are joules per kilogram or kilojoules per kilogram. But we can put them together. So you've got the total energy to melt is specific heat times mass times the change in temperature up to the melting point, and then you've got mass times the latent heat to give you the energy for the rest of that. So I did have a couple of examples in here, but just because I'm trying to give you a little bit more on the material side of this, I'm going to leave the examples until the last minute. So we've got a few different theoretical melting energies. You can see, for example, there, iron with a melting temperature of 1600 degrees requires a theoretical energy of melting of 0.391 kilowatt hours per kilo. So this is just pointing out what I showed before. So if you have an alloy, so this is an alloy here, a very simple alloy, which literally has a copper nickel, and with the copper nickel phase diagram, you've got a very simple phase diagram which looks a bit like a lens shape. This is about the simplest phase diagram you can have. So when the nickel content is 0, we've got the copper melting point. When the copper content is 0, you get the nickel melting point, and everything between there, you've got an absolute solid state mix between a solid solution mix between the two of them, which means that it goes from being there's only the one change between the two, but you can see if you were to take a cross section there at a given nickel percentage, that you've got this freezing range which starts at the liquidus and finishes at the solidus. Right, so crystal structure. So most metals are crystalline in structure, and you can see some of the defects that you get from casting, some of the crystal structures you get from casting an ingot happening here. You can see quite clearly the defect when you try to casting a cylinder has got to be one of the hardest things to actually cast, which is funny, but you can see the piping where you've got shrinkage coming down the middle of it, but you can also see the orientation of some of the crystals of the metal as they've grown away from the boundaries of the casting. So you get equiaxed and columnar are the main two types of crystal. When you get a very rapid reaction, very small crystals form and nucleate close to the cooler boundaries. So when there's a high temperature, and at that point, then you've got a slower solidification, and you've got the cooling rates tending towards the middle, where then it sort of finally solidifies. And you can see that the predominant direction that the crystals take on this bottom image animation here, you can see it forming equiax crystals all the way around the boundary, kind of like here. Then you've got a very set direction where the crystals want to grow in one single direction along the cooling curves, and then in the middle you've got a repetition of the equiaxed all happening down the centre line. So with higher cooling rates you get more kind of disparity between the columnar and equiax. Equiax will tend to happen more when you've got something which is more of a sort of steady state cooling, lower cooling rates. But it's important to know the differences between the two, because they do affect the properties. So we'll see a few examples now from the different processes where they've been cross-sectioned, and you'll see those crystals on a small scale. So predominantly what we have is a columnar grain direction coming into the base plate. So you've got all the heating is going down to the base plate. So you've got a lot of long columnar growth, and that's happening in all these different methods, whether it's the electron beam, the laser powder bed. We do get equiax grains, and if you do get equiax, and sort of traditional aerospace materials like to have, whether it's through cast or forged or whatever, they like to have very small equiax grains in all, so that you get a very isotropic set of mechanical properties. And that's unfortunately what we don't get. So a lot of the anisotropy of the mechanical properties from additive manufacturing it's been linked to this orientation of the columnar structure. And this affects, for example, tensile tests. So that, let's see some examples there. So for electron beam, and you can see here that these grain structures are actually quite large. So we've got 0.5 mil, almost a millimetre, and you can almost make out the grain structures by eye. So these have been prepared by through a technique called EBSD, but it shows you that predominantly you're getting a lot of long grains coming down through the materials in the direction of the build, so or opposing the direction of the build, if you wish. So these are some of our own images from the powder bed, which show a single melt bead upon previous layers. And you can see that although we do have some equiax, particularly at the end part, at the top of the, so if you think of this forming and solidifying away from the boundaries, and the very last place to cool would be the top of this melt bead, and you get a bit of equiax structure up at the top of there. But on the whole, all of these grains that are trying to form their way back down to the base plate, which is at the bottom of that. So this is by a paper from Cho from just earlier this year, and it shows a range for the powder bed SLM which they worked on, and they did some analysis on the parts they made to work out the temperature gradients that they were getting, and then they used some of theoretical estimates of when you would get fully columnar or mixture or fully equiaxed, depending on the different cooling rates. And they found that their window of work was always there, so it meant that they would always have, because of the cooling rates in there, fully columnar growth. So just to show that it's not just E-beam and powder bed, this is some work was done at Cranfield University on a project we run with them. And you can see here that again we've got quite large grain structures and quite large structures actually. So we're talking 5 mil by almost 25 mil, and you can see the grain structures running through them vertically down. So you've got two different types. You've got the left there is a laser clad, a cross section through a T section of a laser clad, where the laser clad's gone back and forward and built it up like that. So the two images on the left are a side view, where you can see all the layers going up, and then it's a cross-sectional view where you can see the melt pool, and you can see the grain structure is kind of dipping down towards the center of the T-bar. And on the right-hand side is a wire arc additive. So the left-hand side used blown powder to build it up, and the right-hand side has used wire and melted it on a wire. And with the wire, you can see a little bit more randomness in the, but still, all the grain structures are predominantly in the vertical direction going down. So one last image to show why it is important to understand some of these thermally induced microstructures which happen on the melt pools. We've got these are deposition tracks for laser deposition. So really quite large melt pools, 5 millimeters across. And here again you can see the predominant columnar structure underneath the melt pool, heading down in towards the previous part of the build, and on top of it that bead, very similar to what we had, except we had it like down at about 100 microns, 150 microns, and they've got 5 millimeters, but you can see that kind of sprinkling of equiaxed growth at the top of it. Okay, was that sufficiently materials for you? Did you hate it, or was it all right? Yeah? Alright, so I'm going to try to rush through this just to give you the overview now on the convection side. So we talked about the Fourier equation being valid for both fluids and solids, but now with convection, so for a solid side, we can get rid of that term there, but when there's fluid in there, we've got transport of heat. So here are different forms of convection that can arise. We have natural convection that you know, so it's a change in density because of a change in temperature. We can have gravitational convection, non-temperature driven density variations, forced convection, when you're literally like blowing a hairdryer that's hot over a wet surface, you can evaporate it, that's forced convection. Marangoni convection, so this results from surface tension different differentials as a function of temperature or composition. Marangoni is something I'm going to talk about a bit more in a minute. Granular convection, so if you have a discrete flow of particles, then you can actually get convection due to different sizes and within the grains. And capillary action, also linked to Marangoni, you can actually get fluid to move through the capillary action, and that's sort of seen as a convection term as well. Natural convection, typically off a surface, like all of these things, all of these convections will arise at surface interfaces between solid liquid and solid gas. So natural convection, I'm not going to talk about it too much, but it does arise. Obviously it's part of, if you've got something which is at 2,000 degrees or 2,500 degrees, you are going to get a small area of influence around that very hot part, which will cause any gases which are next to it to want to rise away from it. Okay. Forced convection is definitely something which we find. So we've got cold gas coming in at ambient and going over relatively hot plates at 170 degrees, or localized hot spots which are right up to 2,000 degrees. So you're going to get a forced convection between that area and the gas. So both of those are important from the perspective of being able to design a cooling rate, a transport rate for the gases, and making sure that you're not forcing any powder out of the way. So Marangoni convection, just to give you an example here, so this can arise if you were to switch off all kinds of natural convection, any thermal convection apart from Marangoni, and you allow a temperature variation across the interface between a solid and a liquid, which may be driven by composition, you can force convection currents in the melt pool. Okay, very small changes, and for example, I'll tell you why it's important. So with 316 steel, you can have even this very small variations in composition, and in an impurity like phosphor, can actually reverse the direction of the convection current within the melt pool. Why is that important? Well, it's important because if you've got the melt pool going round in the same direction that coincides with the laser going down, you're actually adding to the depth of the melt pool. So say you have that small variation of phosphor mixture go the other way around, okay, so it switches direction, it's going away from the laser, you end up with a wider melt pool which isn't so narrow. Okay, so it has a big effect upon how you would select your material your machine properties. So you would choose a wider hatch spacing for one, or a narrow one, and you might want to have to set different powers to make sure that if you're getting Marangoni convection, which assists the flow of the melt pool down, that it doesn't go too deep and form a keyhole. So to avoid that, and it's only very, very small differences in phosphor which can cause that. So knowing that, in fact not phosphor, sorry, sulfur. Right, but you can see there, the image on the left has gone, even though it's 0.026% of weight and 0.07, you can see a very big difference in the predicted melt pool patterns. And this is seen in practice, and it happens with much larger weldings when you're welding 316, but with a proper weld as opposed to like a tiny little. But it happens with on our scale as well. So all of those things I've told you about today, they're important for additive, and you've got to try to take all of those into account to a little extent, or know a little bit about them. So anything that affects the melt pool, the width, the depth, the length, will ultimately affect how each single track is formed. Okay, so these are some simulations, but it does show. There's some experiments. I think the ones on the top of the experiment, one one's the simulation, and they are predicting the grains through a Monte Carlo method, and you can see these longer grains with this type of scan direction, and then slightly shorter, but still columnar, but with some equiapsed regions in there as well. So they're important. Convection is important as well. So of all the radiative heat transfer is important, the convection is important. Particularly convection is important because of this Marangoni effect. The width and the height of the melt pool are quite variable. It's not something that are easily predicted. Small changes in composition can change them. And that will obviously, the differences in the, so if you've got a melt pool with a very long length, short width, you're potentially going to end up with balling. So that's something you want to avoid. But it would also potentially affect how we remelt lower surfaces. So if it's going in deeper, then it's remelting below, and then you're also going to affect that columnar structure of crystals which are forming on the way down towards the plate. And obviously then the convection does have a role with the gases into how much can get entrained. So when you're at that very high power density where you're starting to get keyhole and you've got gases coming in, that convection is also going to determine how much extra porosity gets formed. So one last section here before I finish up is just conduction, and I'm only going to breeze through this because it does have an effect. And it's probably the least clear of how strong that effect is. We just know it does affect it. Powder itself can be used as an insulator in panels in space. They'll often fill a panel with powder to make it in. So metal powders are actually really good insulators. They're very low thermal conductivity. Now if you think about it, you've got a powder bed and you've got a component in the middle of it. The heat's not going to want to go through the powder. It's going to go through the component. So the only thing that you've got to get that heat away from the component is the component itself that's been pre-built, and then also maybe some support structures that you put around it. All right? So, and there'll be variation in thermal conductivity of the support structures. There's a variation with temperature of the thermal conductivity of the part as it goes down towards the plate. But that will determine how that connection, if you like, between the grain structure as it goes through. So the conductivity itself, how much heat it can whip away, determines the absolute magnitude of the cooling rates, and therefore also affects the microstructure. That's the theory. The reality is actually quite difficult to disassociate any of these heat transfer mechanisms from each other. It's very, very difficult. So most of the models that you see about additive at the level of the melt pool and building up melt pool layer by layer, they often have very complex multi-scale, multi-physics all built in because they just can't detach any of them. So I did say at the beginning that we're trying to get somewhere with a reduced physics model which only does no flow, for example, and it works to a certain extent, but powders, I did have some theory here about powders. I'm not going to go into it. It's a bit detailed for today, and we get this finished now. But it shows that you can sort of predict the thermal conductivity of powders. As the particle sizes come down, your thermal conductivity comes down, and as the sort of packing of those powders becomes looser, then so as it becomes tighter, then you also get a lower thermal conductivity. But I'm not going to go into that. So anyway, just to repeat what I said. Low thermal conductivity of the powder and the thermal conductivity of the as-built material, which includes the structures, determine cooling rates through the layers. And the cooling rates have a big role to play in the directionality and therefore the anisotropic nature of the material. Okay, that was all I'm going to do. I told you it was going to be a long one. You wanted lectures, I gave you lectures. I'll put it up on Blackboard so you can bore yourselves to death with it later on. Any questions on any of that? Did you manage to have a go at the test that I set? I noticed yesterday there wasn't many people who had done it, so was it okay? Yeah? We covered that in enough, I thought, in enough detail that if we step through it, it shouldn't be too hard. Okay. All right. Well, I'll see you on Thursday. Yeah?